Performance testing of hydropower plant. Hydropower or hydroelectric power is a renewable type of energy that creates power by utilizing a dam or diversion construction to modify the natural flow of a river or other body of water. Hydropower relies on the unending, constantly replenishing system of the water cycle to produce energy using fuel water that is not diminished or eliminated in the process. Hydro energy is created in a process that starts when water flows through a dam. The water behind the dam moves through an intake and subsequently turns blade in a turbine. The turbine spins a generator and produces electricity. The amount of electricity generated depends on how far the water drops and how much water moves through the system. The electricity can be transported over long-distance electric lines to homes, factories, and businesses. There are three main types of hydropower technologies that includes impoundment, diversion, and pumped storage. These varying types of technologies are illustrated throughout, as well as marine hydrokinetics, which includes wave, tidal, current, and thermal technologies. Hydropower plant also has advantages and disadvantages. So for the advantages of hydropower plant, it is renewable because it is powered by water, and water is naturally replenishing resource. Production of hydro energy doesn't involve burning fossil fuels like coal or oil. It doesn't produce emissions or harmful chemicals that pollute the air. It is the cheapest way to produce electricity, and it's a renewable energy source. Hydroelectric energy also doesn't produce carbon dioxide, the element responsible for the greenhouse effect, which is thought to be the reason for climate change. Once a hydroelectric complex is constructed, the project produces no direct waste. And last, hydro is a flexible source of electricity since plants can be ramped up and down very quickly to adapt to changing energy demands. For the disadvantages of hydropower plant, dumping rivers may destroy or disrupt wildlife and other natural resources. Second, hydropower plants can also cause low dissolved oxygen levels in the water, which is harmful to wildlife, ecosystems, and, in some cases, agriculture. Next, the installation and maintenance costs associated with hydroelectric plants can be extremely costly. Initial capital outlays can be serious obstacles. Next, the ability to create electricity can be severely reduced if there is a drought and not enough water is flowing into the plant. Main elements of hydropower plant. Each of these fundamental components has a size, location, and kind that are determined by the topography, geological conditions, and water usage. So the first element of hydropower plant is the storage reservoir. It is a necessity for a hydroelectric power plant. It assists in supplying water to the turbines in accordance with the load on the power plant by storing water during periods of surplus flow and supplying it during periods of lean flow. Next is dam. The purpose of a dam is to offer pondage, storage, or the ability to divert water into conduits in addition to raising the stream's water surface to create an artificial head. The most costly and significant component of the hydro project is a dam. Dams are constructed using earthen or rock fill, concrete or stone masonry. Next is forebay. The forebay functions as a control reservoir, temporarily storing water during the periods of low load and providing the same for initial increases due to rising load, during which time water in the canal is accelerated. Next is the spillway. This was built to serve as a safety valve. When the reservoir is full, a situation that typically occurs during floods, it releases the excess water to the downstreams. These are typically made of concrete and have water discharge opening that can be closed off by metal control gates. Next is storage tank. The storage tank, a storage reservoir, is typically placed as close to the power plant as feasible, ideally in the ground to lower the tower's height. Next is the penstock. The forebay or surge tank is connected to the turbine scroll case via a closed tube. Each unit is typically given in its own penstock in medium head power plants. A single penstock is usually utilized in high head plants, and branch connections are offered at the lower end to supply two or more units. Next is the valves and gates. Gates at the entry of the tube casing are typically all that are required in low head facilities to stop the flow and allow for the unwatering of the turbine to inspection and repairs. Trash racks. These are constructed from a series of long, flat bars that are spaced so that the minimum width of water can travel through the turbine. Tail race. After serving its purpose in the turbine, the water is released into the tail race, which may take it to the same stream or another. The size and design of the tail race should allow for the unfettered escape of water and unrestricted passage of the water jet after it leaves the turbine. Draft tubes. A draft tube is a conduit that is appropriate diameter that is joined to the runner outlet and carries water from the well down to the tail race where it is discharged beneath the water surface. And last, prime movers or the water turbines. Water turbines are employed as prime movers in hydroelectric power plants. They convert the kinetic energy of moving water into mechanical energy, which is then utilized to power the alternators that produce electrical energy.
Rationally, hydropower systems generate electricity or mechanical energy by harnessing the energy of moving water. Because hydropower plants can generate power to the grid immediately, they provide essential backup power during major electricity outages or disruptions. Hydropower provides benefits beyond electricity generation by providing flood control, irrigation support, and clean drinking water. Hydropower is affordable. Figure 6 shows a typical hydroelectric plant as a cost-effective alternative to expanding the energy grid. Micro-hydro plants are particularly useful as remote area power supply for rural and isolated areas. The system offers a source of low-cost, independent electricity that is available continuously and doesn't harm the environment. Theoretical background. Brake power. Brake power is the amount of power measured using a brake-type dynamometer at a specific point, such as the crankshaft, gearbox, output shaft, rear axle, or rear wheels. Obtained brake power by using the formula PB or the brake power equals to pi nt over 60,000, where N equals revolutions per minute, T is the brake torque in Newton millimeter, PB or the brake power in watts. Turbine efficiency. The hydraulic power is the next energy transferred to the water per unit time. The input power delivered by the motor to the pump is called the brake horsepower. The difference between the brake horsepower and hydraulic power is the pump efficiency. Obtained turbine efficiency by using the formula. Enter the turbine efficiency equals PB over PW times 100%, where NT is the turbine efficiency, PB is the brake power, and PW is the hydraulic power.
Review of related literature. Hydroelectric power captures the energy released from falling water. In the most simplistic terms, water falls due to gravity, causing kinetic energy to be converted into mechanical energy, which in turn can be converted into a usable form of electrical energy. Ancient Greeks used wooden water wheels to convert kinetic energy into mechanical energy as far back as 2000 years ago. In 1882, the first hydroelectric power plant was built in the United States using the fast-flowing river. Humans in that time began creating dams to store water at the most convenient location in order to best utilize power capacity. In their study, laboratory model of small hydropower, Sladik and others, two asynchronous motors were used by the plant, the first of which served as a motor and the second as a generator. This HPP model also had number of pressure gauge and electronic flow meter for detecting non-electric values. For the control of the SHPP, understanding the relationship between the hydrodynamic, mechanical, and electrical characteristic were crucial. Another study by Anido and others aims to collect data by employing device and gaining the brake power that can be used to generate electricity as well as to use wasted potential energy from rainwater and convert it into mechanical energy with the use of turbine. Their study also aim to assess the type of turbine and to use referred to previous studies and through simulation. In their laboratory setup, they used the tested three different kinds of turbines which included Pelton, Turgo, and cross-flow turbine. Hydropower generation. Water's energy has traditionally been harnessed by hydropower system to produce mechanical work. Grain milling was just one of the industrial processes that these systems were employed for. Modern hydropower systems convert the water stored energy into electrical without the use of mechanical effort. Storage hydropower. Storage hydropower system makes use of the water potential energy that is trapped by a dam structure. To produce energy, water is released from the dam and passes through the turbine. The rotating turbine activates a generator to produce power. Pump storage hydropower. Pump storage hydropower system move water back and forth between upper and lower reservoirs to provide peak load supply as opposed to storing hydropower. When electricity is needed, water from the upper reservoir is released spinning a turbine. Offshore hydropower. Offshore hydropower plants generate electricity using the water waves and tidal currents. Offshore hydropower is still expanding even though it is the newest of the several types of hydropower. These categories include technology like buoys, underwater turbines, and Vibrating water columns. Runoff river hydropower. By turning a turbine with water flowing from a river or channel, river hydropower creates electricity. The kinetic energy of moving water is used to produce electricity as opposed to storage hydropower systems, which rely on potential energy as their primary energy source. Turbine. A turbine is a rotating mechanical device that transforms the energy contained in the fluid flow into productive work. When a generator is added, the work that a turbine produces can be used to create electricity. Turbines can also be separated into impulse and responsive turbine based on how they operate.
Methodology. Physical laboratory setup made ready by Anino et al. In accordance to the research was utilized in this experiment. The actual setup is located in Baclayon, Bohol. Below is the picture of the actual setup. Components of the setup. Water reservoir, where the water is stored in order to be reused. The gate valve. It is used to completely shut off fluid flow or, in the fully open position, provide full flow in a pipeline. It is used to adjust the flow rate of the water. The water pump. It moves the water through the pipes by mechanical action, typically converted from electrical energy into hydraulic energy. The pressure gauge. It is an instrument for measuring the condition of a fluid that is specified by the force that the fluid will exert when at rest or when at rest on a unit R such as pounds per square inch or Newton per square centimeter. The power indicator. It indicates that the machine or setup is functional and is ready to be used. The circuit breaker. It is an electrical safety device designed to protect an electrical circuit from the damage caused by an overcurrent or short circuit. The load cell. It is a force transducer that converts force such as tension, compression, pressure, or torque into an electrical signal that can be measured and standardized. And for this setup, It is powered by an Arduino Uno, a Pelton turbine. This is an impulse blades that are often tangential to the turbine. This is the turbine used in this experiment. Each blade is made up of two buckets that are joined in the middle. The nozzle. It is the guide mechanism that directs the flow of rainwater into the blades of the turbine. The liquid crystal display or the LCD. It displays the angular speed and torque of the turbine being measured. The flow meter. It is a device that measures the amount of water flowing through a pipe. The panel board box. It is where the Arduino Uno and the photointerrupter connections is placed. The photointerrupter acts as a tachometer, measuring the shaft's rotations per minute. The parameters to be obtained are the torque, angular speed, and brake power. Torque can be obtained from the load cell measured using an Arduino Uno and has a unit of Newton millimeter. The angular speed is measured using a tachometer and controlled by an Arduino. Brake power is obtained using this formula. EB is equal to 2 pi nt all over 60,000, where N is equal to the revolutions per minute, T is the brake power in Newton millimeter, and PB is the brake power in watts. Procedure. Water drawn from the reservoir was utilized. A pump moves the water through the pipe. A gate valve regulates the water flow. The flow meter and the pressure gauge records the flow of the water. The nozzle was placed to align to the Pelton turbine. The LCD displays the torque and the angular speed of the turbine. Flow rate was adjusted to desired flow using the gate valve. Data was recorded for the angular speed and torque for a specific flow rate. Brake power was computed.
Kung gusto mo, daan. Results and discussion. Data gathered. During the testing done by the group using the laboratory setup of Anino and others, the group acquired the following results as given in the table 4.1. Table 4.1 is the data obtained from testing. The parameters are angular speed in RPM, torque in Newton millimeter. The flow rate per gallon below are 5.4, 5.9, 6.3, 8.1, and 9.2. For the 5.4 gallon per minute, the angular speed are 300 rpm and 156 torque in Newton millimeter. From 5.9 gpm, the angular speed are 480 and torque is 150. And 6.3 gpm, 720 rpm and 144 Newton millimeter. For 8.1 gpm, the angular speed is 1080 and the torque is 117, and for 9.2 gpm or gallon per minute, the angular speed is 1260 and the torque is 107. Brake power of the turbine. The group was able to calculate the amount of brake power that a turbine would have at each different flow rate. Table 4.2 shows the summary of the calculations. Table 4.2 shows the brake power for different flow rate. From 5.4 GPM, the brake power is 4.9 watts. For 5.9 GPM, the brake power is 7.54 watts. For 6.3 GPM, the brake power was 10.86 watts, and for 8.1 GPM, the brake power was 13.83, and from 9.2 gallon per minute, it was 14.12 watts. To further analyze and interpret the results, the valuation in the tables. Torque and angular speed at different flow rates. Figure 3.2, torque at different flow rate. Figure 3.2 shows the graphical representation of the torque measurement at different flow rates. It shows that as the flow rate of water increases, the torque of the turbine decreases. The maximum torque obtained was 156 Newton millimeter at 5.4 gallon per minute of water. Figure 3.3 shows the graphical presentation of the angular speed at different flow rates. As the flow rate of water increases, the angular speed of the turbine also increases. Highest angular speed was obtained at 9.2 gallon per minute with a speed of 1260 rpm. It can be concluded that the relationship of the torque and angular speed of the turbine is when the angular velocity increases, the torque of the turbine decreases. Brake power versus flow rate. The calculated brake power at different flow rates was presented in the figure 4.4. The maximum brake power obtained was 14.12 watts at a flow rate of 9.2 gallon per minute. The brake power of the turbine increases as the flow rate of water also increases. This is due to increase in hydraulic input power of the water to the turbine, which results into increase in angular speed of the turbine as presented in figure 3.3. Conclusion. The experimental setup was designed to test the capability of water flow to produce turbine brake power, which can be a potential source of electricity. Maximum angular speed of 1260 rpm was obtained, having a torque of 107 Newton millimeter, resulting to a maximum brake power of 14.12 watts at a flow rate of 9.2 gallon per minute. The brake power and the angular velocity is directly proportional to the brake power.